8.1. Find angle measures in polygons. First, we have to do a little bit of work as far as what is a convex polygon. So how do you find a missing angle measure in a convex polygon? First of all, a convex polygon is a polygon without a dent in. So there's an example of a convex polygon. Okay? A diagonal. A diagonal looks like this. Of any polygon, a diagonal is this cross segment, so to speak. Okay? Diagonal is also used to kind of describe a line that's not horizontal or vertical. So a diagonal, a segment with endpoints as non-consecutive vertices. Okay, so here's an endpoint, here's an endpoint, here's a diagonal. Okay, interior angle. The interior angle is an angle on the inside of a polygon. So an inside angle of a polygon. Alrighty. And then an exterior angle. These look a little different. There's actually interior sets of angles, so if I would extend, and extend, here's a set of exterior angles right here. So really it's an outside angle of a polygon. So those are our definitions for vocab here. I've got kind of things marked on the figure. Let's proceed. We do have a theorem to start here. Interior angles theorem for a polygon. What happens is, if I have, let's say, a pentagon, okay, and I go ahead and from one vertex draw the diagonals, I get 1, 2, 3 triangles. So I would get 3 times 180 for the total number of degrees. So if we have n sides, that means we're going to have n minus 2 triangles. So n minus 2 triangles, and each triangle is in 180 degrees. Alrighty. Examples. Find the total here, 180, 14 minus 2. Parentheses required, multiplication is commutative, so it can go either way. So 180 times 12, which comes out to be 2,160 degrees. Over here, a little simpler. My n is 4, or I could just put a diagonal here and say, hey, I got 1, 2 triangles. So 2 times 180 equals 360 degrees. Moving on. With that, 360 degrees. Every quadrilateral, as long as it's convex, will have 360 degrees. And why that is that each quadrilateral has 2 triangles from the diagonal. Let's fix this here. From the diagonal, thus 360 total continuing here. There's some additional problems here. Now here they give us the total. They want us to find the number of sides and then name it. So this has to equal 180 n minus 2. A good step here is to divide by 180. That's one way to start. N minus 2 equals 12. Add 2. And we get 14 for n. And we call that a 14 gon for the name. Over here we set this equal to 180 minus 2 product. Divide by 180. I'll just do this all in blue here. 1 minus 2 equals 10. Add the 2 over, and equals 12. And once we have that, we know that we can call it a dodecagon. Dodeca. Or you could call it, I guess, a 12 gon would be okay. This is the better answer, right there. Problem here. Try to figure out the convex polygon's value for x. Again, I'm going to count 1, 2, 3, 4, 5, 6, 7 angles, so n equals 7. Very important, because the total degrees will be this. And now if I've got my 2x terms here, that's 3x altogether. And when I add this, 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 and this, I end up with 645 degrees. Over here I can change this to 5, so now I get 900 equals 3x plus 645. Subtract the 645 over, and we get 255. Divide by 3, and I get 85 degrees. So x ends up being 85 degrees. Now, as we talked before, we have exterior and interior angles. Exterior angle set again. Let's just take a quadrilateral. Extend, 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 and extend. Here's my exterior set of angles. And no matter how many sides you have, this is a constant of 360 degrees. The reason for that is, if we take a look here, we got 180 degrees there, 180 degrees there, 180 degrees there, and 180 degrees there. Those green arcs represent 180 degrees linear pairs. So I have 4 times 180 minus, since it's a quadrilateral, I get 2 triangles, so minus 2 times 180. That equals 2 times 180, which gives me 360. And that occurs and works for any type of convex polygon, regular, non-regular. So as we transition to a problem involving this, we can go ahead here, and again, I have an exterior set of angles, 1, 2, 3, 4, 5, 6 of them. Counting them doesn't really matter because it's always 360. So I know that 360 will equal the sum of these 6 pieces. But let's combine this with this for 3x. Let's combine this, 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 and this, these other exterior angles, for 252. Subtract, equals 108, divide by 3, x equals 36. A little bit easier than the other way as far as interiors. But again, still some algebra involved there after the initial setup. couple things here, and then we'll go and deal with the end of the lesson. Problem A6 here, regular heptagon. Heptagon, we have to remember, is 7 sides. I need to find the interior angle measure, so 180. Number of sides minus 2 divided by 7 angles will give me 128.6 degrees. For my exterior angle for this regular polygon, remember, regular polygon, all sides are the same, all angles are the same. Again, if I did a regular pentagon, it would maybe look like this. I go ahead and do this. First of all, these are all the same. These sides are all the same. And these exterior angles will be all the same. So here I got 360 for exterior divided by 7 will come out to be approximately 51.4 degrees. Similarly, a nonagon is 9 sides. Again, my interior is going to be 180. 9 minus 2, all divided by 9. That comes out to be exactly 140 degrees. My exterior, 360 divided by 9 is 40 degrees. Little side note here, if I take the 140 times the 40, I get 180 degrees. If I add these two up, I get 180 degrees. So we can tell again from here, our little sketch of a regular polygon, that these two will in fact always equal 180 degrees, a linear pair. Finally here is looking at some names here. Three-sider is a triangle. 4 sides, quadrilateral. 5 sides, pentagon. 6 sides, hexagon. 7 sides, heptagon. 8 sides, octagon. 9 sides, nonagon. 10 sides, decagon. 11 sides, undecagon, like uno, undecagon. And then 12 sides, dodecagon. That concludes the formal part of the lesson.